Hi, this is Professor Valerie Mueller again, here to talk about linear and nonlinear transformations. To give you an overview of the chapter, basically the concepts I thought were important were the linear transformations and the nonlinear transformations, how they affect the shape of the distribution and summary statistics, and also common transformations being the z-scores for the linear transformation case and the square root and logarithm functions for the nonlinear transformation case. What is a linear transformation? Well, the above formula is the general form of a linear transformation. You can multiply or divide the variable by a non-zero constant k and add or subtract by another non-zero constant c. Why is this useful? It's useful for rescaling old variables into other denominations, and there's several reasons provided in the book on why you might want to do that. Multiplying old variables by a non-zero constant has this really nice feature that the medians, means, and modes of the new variable distribution are simply a multiple of the respective statistics from the old distribution times that constant. So you can see if you know the median of the old distribution and you multiply that variable by k, then the median of the new distribution is simply going to be k times the median from the old distribution. Measures of spread are similarly affected, except you multiply by the absolute value of the constant for the case of the interquartile range, the standard deviation, and the range. And you multiply by the square for the case of the variance. The effect on the measures of shape vary depending on whether k is positive or negative. If it's positive, you have the same skewness metric and skewness ratio. If it's negative, you have the same skewness and skewness ratio metric, except you multiply it by a -1. To see how the linear transformation affects the shape of the distribution, look at the first box plot on the left for the variable self-concept in 12th grade. You can see that the distribution of the variable is rather compressed. The middle box plot multiplies the same variable by 2. You can see that the values have been stretched. The box plot on the far right multiplies by a value of -2. Here, you can see not only have the values been stretched, but they've been shifted in a negative direction. Adding old variables by a non-zero constant c has this nice feature that the measures of spread and skewness are preserved. To find the measures of central tendency, you simply need to add the same statistics of the old variable by that non-zero constant c. To see how the linear transformation affects the shape of the distribution, have a look at the figure in this slide. First, look at the first box plot on the left for the variable self-concept in 12th grade. The middle box plot adds the variable by 5. You can see that the values have been shifted in a positive direction along the axis with no change in the spread of the distribution. The box plot on the right subtracts the old variable by a value of 5, and here the measures of spread again are retained, but the values have been shifted in the negative direction along the x-axis. The z-score is calculated by this formula. In particular, you subtract the actual value by the mean of the variable and divide by the standard deviation of the variable. The interpretation of the z-score is in terms of standard deviations, so it's very useful because it allows you to compare the value relative to other values in the distribution. It also provides an easy way to detect outliers. Basically, if the z-score is above 2 or below -2, you can typically consider those values as outliers. I ask you to do a simple calculation of a z-score in the study questions to show you how the z-score can be applied to assess whether the achievement scores of a particular girl and a particular boy in the sample are relatively decent relative to other girls and boys in the sample. Nonlinear transformations are particularly useful when you have a skewed distribution and you're interested in maintaining the order of the values in the distribution. Sometimes we worry that if we have a skewed distribution, our insights might be influenced by a few of the extreme values. So what we do is we try to evaluate the data using a nonlinear transformation of the variables so that our insights are not driven by a few outliers. The most common nonlinear transformations are the natural logarithm and the square root. Their main limitations are that they cannot be used for all values of the variable. So, for example, square roots are only defined for values greater than or equal to 0. Logarithms are defined only on values greater than 0. So if we want to use the logarithm, but we have 0 values in our distribution, we oftentimes add a value of 1 to all of the points of that variable before transforming it. In the first table, just to give an example of a nonlinear transformation and how effective it is, in the first table, I've tabulated some summary statistics of the variable expected income at age 30. And you can see that the distribution is positively skewed. The skewness value is large and positive. In the second table on the slide, I transform the income variable by taking the square root and the log. And the square root transformation actually reduces the skewness of the curve. The skewness metric changes from a value of 10.9 in the original table to a value of 3.7 in the second table. Anyways, these are a few concepts that I thought were important to review. I encourage you to take advantage of the numerous examples provided in the textbook. In the next lecture, I will refresh concepts covering Chapter 5. I'll also provide another short video which will demonstrate how to code the transformation of variables in Stata. Anyways, good luck. Hope you're having a good week.